So hopefully you had a chance to reflect on this exercise, since I'm now going to spoil it. Okay, so this is the way I think about it. What we could do is we can create first this comparator, and we create a min PQ of unharmonious texts right here. Then what we do is we go through, we wait 24 hours and go through all the messages that we see and add them one by one to our unharmonious texts object, right? So in other words, we're going to take our sock and we're going to add the items one by one to it. And here's the really tricky and interesting part. If at any point the number of items in that sock exceeds m, so now I have a sock with like m things in it, then I'm going to go in and I'm going to take the smallest thing out and throw it away, leaving me with the m largest things. And so each time my sack only holds at most m thing or m plus 1 things, and I'm always throwing away the smallest one. And as a result, when I'm done, at this point, the sock contains only the m largest things in the entire day's logs, and then we just create a list of texts that we've seen so far. We go through our unharmonious texts sock, and we add each of them to the list. And the way we do that is just removing them one by one. And in this case, we don't really care what order they're in, so that should be fine. And in this case, once we're done, we return the text list. So what that does for us is it lets us track the top m transactions using only m memory. And this is a very common little trick with priority queues. Maybe you'll even get asked that exact question in a job interview someday. Maybe. Bring a sock. The API for the minimum priority queue essentially not only makes this efficient, but it also makes it very simple to code up, right? I mean, it's a little bit of work here, but you don't need to do any explicit comparisons. I mean, it's a little more complicated than the naive solution, but it's still pretty good. So how would we implement a priority queue? Well, there's a bunch of different possibilities out there. One of them is we could use an ordered array, right? So how would we actually build the sock? An ordered array is one possibility, but in that case, anytime we wanted to add or remove the smallest item, we would have a theta n operation. And this is theta n because you have to resize the array potentially, and in this case, remove smallest, same deal. You might need to resize the array. So this is the worst case runtimes. However, getting smallest will be very fast. How about a bushy binary search tree? Well, if you think about what this would look like, and this is actually a pretty interesting exercise, and so I encourage you to maybe think through how this would work exactly, but we could implement the sock with a bushy binary search tree. In that case, adding will always be log n, getting smallest will be log n, and removing smallest will be log n. But the only big issue is that the way we designed binary search trees is we said you could never have duplicates. And so what that means is that if this screwdriver happens to be of size, let's say exactly 14, and this happens to be also exactly 14, and I put them both on my sock, it will not work nicely with the binary search tree. There's no way to have two copies of the same thing. So you can adapt the binary search tree idea to allow duplicates, but it's just not quite as nice as the idea we're going to have known as a heap. The next natural thought will be using a hash table, but it turns out a hash table is actually just a piece of garbage for this purpose, because if you actually have a hash table, that is an array where you buckets, adding will be really quick, right? You just throw it in the hash table. But getting the smallest thing is going to be slow, because you don't know which bucket the smallest thing is. This is in. So basically what you'll have to do is go to each bucket, look through the whole bucket, go to the next bucket, go through the whole bucket, go to the next bucket, go through the whole bucket, and that's just going to be a waste of time. So what we're going to do with heap is get as good performance as the bushy binary search tree, but in this case, we'll have no ugly caveats. Okay, so we'll do that in the next little video.